Ladies and gentlemen, this class recording. This class recording has started. So, today, we will get started on the next part of this unit. The next part of this unit is titled stoichiometry, which is a fun word to say, lots of syllables, and so if you say it, it'll make you sound smart because if you use big words, people think you're smart, right? So, what? Well, yeah, it might also sound like you made it, like that's not even a word. Stoichiometry, you just made that up right now. Like, no, it's for real. So, like it says in the subtitle, mass and quantity relationships among reactants and products in a chemical reaction. All right, so you see that that's the first thing on your outline that fill in there, right? So today we're going to start in, we're still analyzing chemical reactions. Substances come together, we add a little energy, right, that activation energy, we rearrange the atoms that were there into new substances, right? Usually a release of energy, not always, but a lot of times, right? Okay. But now, like I've told you, a couple times here at the beginning of class, we're looking at it quantitatively. So instead of just what is there at the beginning and what is there at the end, how much is there at the beginning and how much is there at the end. Okay? So, the presentation is kind of boring, white and black today because we're not going to do a whole lot of notes. A lot of it is doing practice things and stuff like that. So don't worry that it's just going to look like this the whole time. So, all right. Stoichiometry. The calculation of quantities of substances involved in a chemical reaction. So, calculation of quantities. So like we said, quantitative analysis. And one important aspect of analyzing a chemical equation or a chemical reaction quantitatively, looking at numbers, is the balanced equation, and especially the coefficients of the balanced equation. So just because we've moved past that section of the unit doesn't mean that we will stop talking about balanced equations. As a matter of fact, they become more important than ever. Okay? And that last part of the statement that's up there, the ratio of moles, that's going to be very important as we go along. Okay? So, let's start off with the chemical equation that you have on your sheet right there. Okay? N2 plus H2 NH3. First, what type of a chemical reaction is this? That is a synthesis reaction. Is it a combustion reaction as well? No, because why? No oxygen in the reactants. Question number, 3. I think I just asked you 3 questions. All right. Question number 4. Is it balanced? It is not balanced, all right? So, and you can see right next to it that in order to balance it, we do this, okay? And that's right on your outline, okay? Good so far. Okay, let's talk about what that balanced equation means. First, we said, why do we have to balance chemical equations? You can give me one phrase. Why do we have to balance chemical equations? That's why chemical reactions happen. Why do we have to balance chemical equations? Yes, that is how they're found. Why is that how they're found? Important concept that we talked about, one of those things we talked about all year long. Well, okay. Yes, valence electrons, that's why it happens. Energy, again, why it happens. Do you have something to say? Conservation of mass, all right? That's why chemical equations need to be balanced, all right? Anything that shows up in the reactants has to be there in the product, right? The first way that we wrote the equation, it looks like a nitrogen disappeared, and it looks like a hydrogen appeared out of nowhere. Can't have that, right? But with the balanced equation, right, everything's there, rearranged from reactants to products, but we have to conserve mass. Anything that's there at the beginning has to be there at the end. Okay? Good so far. All right. So, N2. What is N2? Nitrogen. Give me diatomic nitrogen. So, it is a diatomic molecule. Okay? Does that term sound familiar? Hopefully. Okay? It's two nonmetals joined together. It just happens to be the same nonmetal joined together. How many diatomic nitrogen molecules does this reaction need? How many molecules does this reaction need? 1. Each molecule has how many atoms? 2, but it's only one molecule. Does that make sense? All right. Hydrogen. How many hydrogen molecules does this reaction need? 3. Okay. How many atoms total is that? 6, but it's only 3 molecules. Does that make sense? Okay. The product of this reaction is called ammonia. How many ammonia molecules do we make in this reaction? 2, right? The coefficients tell us the number of molecules that are made or needed in this reaction. Good there? Okay. Now, can we isolate a single molecule of nitrogen, 3 molecules of hydrogen, and produce 2 molecules of ammonia? Because that's what those coefficients mean, right? Can we get 1 molecule of nitrogen, 3 molecules of hydrogen, and make 2 molecules of ammonia? How big's a molecule of nitrogen going to be? Well, what's in it? How many nitrogen atoms? 2. Can we isolate 2 atoms of nitrogen anywhere? It's really hard for us to do, right? Molecules are very small. However, we worked a way around this earlier in the year when we talked about the mole. All right? You remember moles from earlier this year. Okay? So, not at all. Do you at least remember that we talked about moles? Okay, good. So, what is a mole? Eric's not going to be able to answer this question because he doesn't remember talking about moles. But what is a mole? Are you having second thoughts, Liam? All right, so let's review mole. Right? Is that good? Do I go here? Nope, that's not what I go here. All right. So let's start. Okay. Does that number look familiar? Yeah. Okay. Anybody remember what we call that number? It's Avogadro's number, or Avogadro's constant. Okay? Same thing. It's significant because this is the number of things in 1 mole of something. Now, when I say things, it could be atoms, or it could be, say again, particles, or it could be molecules, or it could be ions, or it could be ice cream cones, or Kit Kat bars, or whatever. A mole is a counting unit. It's always the same number of things. Okay? regardless of what those things are, there's always the same number of them. Okay? Does that sound familiar? Okay? Now, when we were talking about, I don't know, let's say copper, we talked about the idea that if we counted out 6.022 times 10 to the 23rd atoms of copper, that would be 1 mole, because that's what a mole is, that many things, right? But for elements, that also led us to something else specific. Do we remember what else it led us to? Let's change one, their molar mass, right? But, Sammy, their molar mass numerically is equal to what? Their atomic mass. Do you have periodic table in front of you? Does Julian have periodic table in front of you? Somebody find copper on the periodic table and tell me what the molar mass of copper is. 63.55. And that's what? What unit would that have after it? Okay. All right. Does that all sound somewhat familiar? Coming back a little bit? Okay. All right. Now, let's use this to our advantage. Okay? This is true for copper. But let's take a look at that reaction that we were just talking about. Okay. Now, I know we don't usually write the 1 in there, but I wrote it in a different color just so we understand that it's there. Okay? Like we just discussed, the coefficients are required for us to balance the equation conservation of mass. But it also tells us how many molecules of each of those things that we need. Okay? But guess what? If it tells us the number of molecules, it also tells us the number of something else. What else might it tell us? Well, how many molecules are in a mole? 6.022 times 10 to the 23rd. It doesn't matter what kind of molecule we're talking about, because moles are a counting unit. So, this is telling us that 1 molecule of nitrogen plus 3 molecules of hydrogen equals 2 molecules of ammonia. But it also tells us this. Okay? Does that make sense? Why numerically molecules and moles are exactly the same thing. The relationship between molecules and moles. Because when we scale up from molecules to moles, we're just multiplying everything by 6.022 times 10 to the 23rd. Does that make sense? Okay. The advantage to doing this is that we can't isolate 1 mole of nitrogen, or sorry, 1 molecule of nitrogen. It's too small. But using what? The molar mass, we can get 1 mole of nitrogen. How many grams of nitrogen would we have to weigh out to get 1 mole of diatomic nitrogen? Take a look at your periodic table. Okay, so nitrogen's atomic mass, or molar mass, done as what? 14.01. But a molecule of nitrogen has how many nitrogen atoms in it? 2. Does that make sense, Don?
Yeah.
So 1 mole of this wouldn't weigh 14.01, it would weigh what? Well, does that make sense? Okay. That would be how many grams of nitrogen we would need to get 1 mole of diatomic nitrogen. Are we following? If you're not following, raise your hand so we can get it. Okay.
Where do you get 20?
Okay, so, Augustin, do you have your periodic table in front of you?
Yes.
Okay, find nitrogen.
Nitrogen.
Okay, what's nitrogen's atomic mass?
14.021.
14.01, okay? And we said that if we had that many atoms of nitrogen, it would be 14.01 grams, right? Just like this is copper, but right? But, just like you said, how many atoms of nitrogen are there in that molecule? There's 2, okay? Good there. All right, now, here comes the tricky part, okay? Let's do the same thing, but let's do it for hydrogen. So, how much does each hydrogen atom weigh? Or what would 1 mole of hydrogen atoms weigh? 1.01, right? Okay? So this is for 1 individual hydrogen. Okay? How much would 1 molecule of hydrogen weigh? 2.02. Okay? But, does that make sense, Gustin? Okay? But, how many molecules of hydrogen do we need here? 3. So, 3 moles of hydrogen would weigh this much. Okay? Does that make sense? Okay? All right. Question. Actually, okay, good.
Why do you put the H to the end of that? You don't put the N to the
Just because I probably should. Because I was being lazy before, I probably should have put that there. Okay. All right. So, now, everyone see where those numbers came from. Okay. How much ammonia are we going to make? Now, there's an easy way to answer this question and a hard way to answer this question. Let's talk about the easy way first, right? 34.08. Eric, how'd you get 34.08? Conservation of mass says that if I start with this much stuff, I got to end with this much stuff. Ooh. Ah. Okay? Okay? We just added. Go ahead.
So like say you mess something up and you get it.
Okay, now let's talk about, go through the same process that we did before. We should get the same answer, okay? So, let's talk about ammonia. How many atoms are in each molecule of ammonia? How many atoms are in each molecule of ammonia? There are 4 atoms in the molecule. Donna, what are they?
Nitrogen and whatever you put in front of hydrogen. 3.
There's 1 nitrogen and 3 hydrogens in each molecule. Does that make sense? Okay? So, we know that the nitrogen on its own weighs this. Each oxygen weighs this. But how many, oxygen. Each hydrogen weighs that, but how many hydrogens are in that molecule? that make sense where I got that from? But how many molecules of ammonia do we make in this reaction? 2. If you multiply 17.04 times 2, guess what you get? 34.08. Okay? So, does that make sense, at least for starters? Okay. Now, let's talk about the mole part of it, because these are all grams. But according to the ratio of the coefficients, how much hydrogen do we need compared to nitrogen to make this reaction work? The coefficients tell us what? Nate, what do the coefficients tell us? What we need, no, how many hydrogens do we need for every nitrogen? 3 to 1, right? That's what these coefficients tell us. We need 3 hydrogens for every 1 nitrogen. But when you weigh it out, is that a 3 to 1 ratio? No. Because each individual molecule weighs different. Does that make sense? You can't compare grams to grams, but you can compare moles to moles, because when we're doing moles, we know we always are talking about the same number of things. Does that make sense? Okay, good.
So say you have,
Sure.
yeah, I just want to.
Okay, all right, well, let's take a look. So, let's take a look at the bottom of your sheet, the bottom of your outline, okay? And it has this problem down here. Okay? Good there? All right. This problem is a little bit close to my heart, okay? Because I don't know if anybody watched the news over the weekend. What? He is coming back pretty soon. That actually wasn't what I was going to... Yeah, there's a guy on the space station who's been there for almost a year, Scott Kelly. He's coming back in a couple weeks, like soon, you know. So anyway, but he's been on the space station for a whole year. They're studying the prolonged effects of being in space and blah, 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 blah. So, but anyway, there was another story that came out that NASA was accepting applications to be an astronaut. Anybody see this story over the weekend? All right, so they had 18,000 people apply to be astronauts. I was one of them. So they're only taking like 8 people though out of the 18,000. So I don't like my chances very much, but I am technically qualified to be an astronaut. So yes, Dave.
Who's gonna be the teacher?
At that point, if I get picked to be an astronaut, that'll be somebody else's problem, because I'm going to move to Houston, because that's where I have to live if I'm going to be an astronaut. So
When do you find out?
they said that they'd make the final decisions like fall of 2017, so like a year and a half. So I'm not holding my breath, like, you know, but I am qualified. Like, I meet all the qualifications. I have a bachelor's degree in a science field. I have a certain amount of qualifying experience after my degree, so, you know, I was like, what the heck? The worst they can tell me is no, you know, so, but, what? I mean, yeah. If they said, hey, do you want to be an astronaut? I would probably go and be an astronaut, yes, so, I mean.
You would leave your family.
No, they'd come with me,
But
like,
like, they come, they went to.
not into space, you know, but yeah, a very small portion of an astronaut's job actually involves going to space, like, you know, so. Anyway,
Mostly training.
say again?
Mostly training.
Yeah, mostly training and like doing research here on the Earth and
What do
stuff.
they do when they're not in space?
They train a lot, and they also conduct tests. of the things they're going to do like on the space station, so that when they get up there in space, they're like, okay, we've never done this before, but here we go, you know, because things can go wrong, and then if things go wrong when you're in space, that's a real problem. You know?
What do they do with the space station?
They do experiments that but the conditions in the space station are obviously different than the conditions here. So one of the things that that this guy who's been in space for a year, there's actually two guys that have been in space for a year, one American guy, one Russian guy. They're studying the prolonged effects, or the effects on your body of being in space for a really long time. It makes you weaker, because when you're on Earth, you're constantly fighting gravity, you know, but in space you're not. And so also too, like, so it makes your muscles weaker because you don't have to work as hard, you know. But also too, it does weird things like, no, it doesn't. It kind of like all the fluid in your body, your blood basically, all has a tendency to go this way, down towards the ground, because gravity pulls it that way. So your body works hard to pump it all back up, like to here and here, because that's where you need it mostly, you know. Lungs, heart, brain, those important things, you know. But when you're in space, that fluid doesn't like all drain to your feet. It just kind of goes wherever, not wherever, but it doesn't like have a tendency to go to your feet. So things start happening, like your eyes get messed up because your eyes like start bulging because there's more fluid here in your brain than there usually is. Like, so that if we really want to send somebody to Mars, like if that's our goal, they're going to be in space like getting to Mars for like 9 months. That's how long it takes to get there. So you're going to have these people that have been in space for 9 months, and then they're going to get there, and they're going to have to start doing stuff. You know, like building shelters and digging and doing whatever we're going to do when we go to Mars, you know? So it was like, okay, well, what's their body going to be like when they get there, you know? A lot of times people who have been in space for that long, they can't walk when they get back to Earth because their muscles have gotten so weak over time that it like takes them a while to build back up. So we're like, okay, we're going to send somebody to Mars, and then they're going to just sit there for a couple days because they can't do anything, you know? Like, those are the things that we're trying to study as we go along. So.
Wait, have we ever found another galaxy?
Galaxies.
There's a bunch of
Lots of
galaxies.
galaxies.
You have ever been in them?
No. So we can barely get out of our own solar system. So, yeah. So, yes.
What would be the point when Earth takes 9 months to get there?
Well, if, you know,
Well, I mean, like,
do we eventually want to live there?
yeah, like that's what I'm saying. What would be the point to like stay there?
Well, if we trash this planet, what the heck? Let's go trash another planet, right? You know, that's a joke, by the way. So, yeah, like that's. I mean, you know, if you ever see Wall-E,
Yeah.
you have like,
Oh, I love Wall-E.
while an extremist view, that is a possibility that our Earth becomes so polluted that we can't live here anymore.
That could probably.
You know, so.
But they end up coming back.
Easy, everybody. We still got like 10 minutes because we're on homeroom schedule today. Yeah.
Actually, we
Augustine,
have
when does second period get done?
51.
Okay, so
5 minutes.
let's talk about this. Okay, so all right. So it says in the space station, carbon dioxide that is exhaled by astronauts can be removed by a reaction with lithium hydroxide. This reaction produces lithium carbonate and liquid water, which then can be used for other productive purposes. So, how many moles of lithium hydroxide would be needed to remove 20 moles of carbon dioxide, which is the average daily amount exhaled by a human? So, going back to your steps, if you go up with this a little bit on your outline. Step 1 to solving these problems. First thing that we have to do, write a balanced chemical equation. That's where this whole thing starts, because we need it to be balanced in order to satisfy conservation of mass, but also to tell us the ratio of things that are going on. So, in this problem, it says, carbon dioxide can be removed by a reaction with lithium hydroxide. So what are our two reactants in this reaction by name? Carbon dioxide and lithium hydroxide. So, I think most of you know carbon dioxide, right? Carbon dioxide is what? CO2. Lithium hydroxide starts with lithium. Hydroxide is what? OH, right? -1 charge. So lithium hydroxide looks like this. Okay? Those are our reactants. Okay? And it says this reaction produces what? Lithium carbonate, so that's one of our products. Here's lithium carbonate. And what else? H2O. So there's our equation. Is it balanced? It is not balancing. H is up on the board. If you don't want to see it, don't look it. Remember, save oxygen for last. Oxygen shows up in a bazillion things in this equation. Save it for last. Yep. Wait a second. Oh, crap. Hold on. 2 there. Okay. That answer isn't on the board, by the way. There's 2 there, right? That makes this 2. That's good. Oh, yeah. Now it's balanced. My bad, everybody. Sorry about that. Jumped the gun. Now it's balanced. All you gotta do is add that 2 there. My bad. All right. Now that we're balanced, now we can start looking at relationships. We'll do that tomorrow, right? Bring these sheets and your calculator and everything back.
What's our homework?